briefly. Pyrimidines, so we know the first step of it, we just have this activated amide, which comes from CO2 and ammonia, but the ammonia was what? Glutamine. Right, and this was this carbonyl phosphate synthase, which we saw where? Urea cycle. So it's an isozyme of that, and this is all in the cytoplasm. I did see that. As opposed to the mitochondrial matrix for the urea cycle. So, which points out what? For the urea cycle, when carbonyl phosphate synthase there, is it using glutamine? No, it's just using ammonia. So it's sequestered from the cytoplasm. Okay, so we form this, we have this activated amide, and then just in one step, essentially, we condense those two atoms with. You said glycine? I'm just shocked. No, because we're going to make the ring, Rachel, in one step, essentially. This carbonyl phosphate, and then we're going to take. So we need to make how many in the ring? 6. We got 2. We need 4. And what's our favorite 4? Spartate or oxaloacetate. And so we have a leaving group at a carbonyl, and we have the alpha amino group of a spartate, match made in heaven, come together. So now we got our 6, and then it just seals up, because the carbonyl phosphate has an amino group at its end. The side chain of the spartate has a carboxylate or carbonyl. Those two fuse, right? So it's just sort of head to tail, isn't it? Like an amine with a carbonyl, and then you have an amino acid, an amine with a carbonyl, and they just flip, and they go head to tail.
Do you want to know about the enzyme that catalyzes reaction?
No. I'm guessing it's
one of them's a regulatory. One of them's a regulatory stuff, though.
Oh, thank you. Yes, absolutely. Yeah, it's okay. ATCase. This is, I don't know. There's some old school biochemist that spent 30 years working on that enzyme. So it's in all the textbooks, and it's just a premier case of this type of. So what type of regulation is this? Feedback inhibition, and almost certainly allosteric in this case. Not sure. Does it say anything about it? Yeah, but feedback. Okay, so pyrimidine. So we made this thing, and then the difference is we made the ring. And now we're going to put on the sugar. Okay, so it just seems reasonable. It was so easy to just form that activated amide, take the aspartate. So it was very easy to make the ring. We didn't need a scaffold to make it. So we just made the ring, and now it can go on the sugar, and you're done. I mean, you make the modifications. It's kind of good to know generally how those are done. Pretty straightforward chemistry. What else? Oh, okay. So now on to probably biomedically the most important aspect of the whole lecture, which is how do you make thiamidylate? Isn't it? Isn't that where we are? Okay. So here's our 1 carbon again that we need to put on. This 1 carbon. And this is a modification, and then, Kim, I think we talked about this briefly after a lecture. I'm not sure I can recount it, but I think you're going to see it again in the molecular biology, why having this methyl group there is so critical. We talked about it some in class. But anyway, it's critical to prevent instability to the genome. So how do we do it? 1 carbon, it's methylene. But it's funny, this carrier has the methylene, but then it has the other component of the methyl group that we're ultimately going to form in another part of the carrier. So it's a carrier of electrons and it's a carrier of a 1 carbon. Kind of weird. But as a result of that, there's two avenues to address for therapeutics, for anti-cancer drugs. So we can address the attachment of this 1 carbon, and we can address the regeneration of the electrons, the replenishment of the electrons that were carried. And there are 2 different types of mechanisms then for inhibitors that have been found to be therapeutics. So what are the 2 types? Suicide and competitive. So it's suicide because it's a substrate analog of the it's an analog of the substrate. It binds a covalent intermediate that can't be resolved because of this the fluoroatom substituent. So it can't be resolved, so it's dead. It forms that enzyme then is trapped in this covalent intermediate, no longer catalytic, taken out. In the other case, it's again a substrate analog, and then the current version is methotrexate, which is an analog of what? Folate, which was the carrier itself. So of the 1 carbon and the electrons. But in this case, we're looking at replacing that hydride ion that comes from what? NADPH. So this is dihydrofolate reductase. So that's a competitive mechanism. I think that's all one need to know about that.
But it's analog to the dihydrofolate reductase, right?
No, it's not an analog to the enzyme, it's an analog to the substrate.
Right, and then it's essentially got it.
Okay. So yeah. So this methotrexate then was the first anti-cancer drug. And this 5-fluoro compounds, what is it, 5-fluoro-DUMP or something, or these are in the clinic. I think they're pretty widely used, as is methotrexate. So now you understand these mechanisms, and the reason we're using them is because this is incorporated into DNA and DNA only. If we inhibited all pyrimidine biosynthesis, we might as well just take cyanide. Right? Is that good to inhibit all pyrimidine biosynthesis? I don't think so. You don't make RNA, you don't make anything. So, not a good drug. Whereas this one is, because you're just you're just slowing down cell division. So this would then be tumor cells. So I guess it can't be that good for RBC. I don't know what other kind of cells turn over. I don't know. I'm a biochemist. So what do? Anybody?
Epithelial cells.
Which epithelial? So your skin?
Yeah, mucus.
Okay. Yeah. Okay. So kind of cosmetic, perhaps, when your hair falls out. Yeah. Yeah. I guess I'd go for hair falling out over the alternative. Yeah. All right. So, God. Okay. So purines. We kind of touched on it. What's the major difference in the strategies? Right. So you start with the sugar. And this is another place where we use glutamine instead of ammonia. Right. We put that first amino group on the activated sugar from glutamine. And then I noticed that Kwame and I were talking about this yesterday. It's essentially kind of like step -1, because steps 1 through 6 was okay. What's the point? What's the common theme there? these ATP GRAS enzymes, right? It's nucleophilic attack by an amine at an activated carbonyl group. And so essentially you do that when you put that amine on from glutamine. So you've got your first amine, because then in the next step, you're going to have a condensation via that amine. And so that just gets repeated over and over again. And then, Rachel, now you can... Yeah, so, you know, I think it's easier to keep straight in your mind that if you just think pyrimidine synthesis, very easy, 2 and 4, you're at 6. In this case, the biggest ring, you're using the smallest amino acid, and that's contributing the most atoms to the scaffold, is glycine. Kind of strange. So glutamine comes in twice, right? It's donating amine twice. We have these formal groups, which are just carbonyls, right? Because all of this is about an amine packing a carbonyl. So this whole thing is made that way. And so those come from not the methylene, but the formyl, the other oxidation state. But as Sarah pointed out, those are coming from serine. We're replenishing those when we make serine, and serine's catabolized to glycine, or whichever way you describe it. Okay, we've got those. What else? There's a CO2 that gets activated. I think that's everything, isn't it? So we have this ATP GRAS business. I don't know. There's some weird rearrangements. Yeah, aspartate, thank you. So, yeah, it's funny. So in this case, aspartate comes in but only donates its alpha amino group, which we saw again where? Urea cycle. And then this is the other common aspect. Then what goes off? Fumarate. And then that can just be part of the TCA cycle. Okay, I think we're pretty much done. Maybe just to segue in, so then we have this balance business, right? So now we're at this common intermediate, but we've got to make AMP or GMP, and interestingly enough, this exocyclic amino group of AMP is again coming from aspartate. So I guess this is the third time then we've seen aspartate donate just its alpha amino group, and fumarate goes off. And then we get to AMP, and then to make GMP, it's I guess it's oxidation reduction. We have to introduce a carbonyl, so we do that. But what really stands out about this forming these two? One. Right, so you use ATP to make GMP and GTP to make AMP, and that balances the pools. But that's great. But so we can have a well-balanced pools, but what if we're just making way, way, way too much of it? We're not regulating the synthesis. So that's where, I think it's the next slide, we see there's yet another level of regulation, which is feedback inhibition. So that's how we get the levels to where we want them. So in this case, is it this cross business, this crisscrossy, or is it feedback inhibition? I mean, is AMP going to regulate GMP synthesis?
No.
No, it's going to regulate AMP synthesis. Okay, and then, so that's AMP, GMP, and you can go even further back where the IMP and the other two can then regulate the earlier steps in the activation. Or I guess it's putting the amino group on the activated sugar or making the activated sugar itself. So you have all of this, you have this extensive feedback inhibition from these purines. Okay, now are we, there was ribonucleotide reductase, we understand that, don't we? Ribo to deoxyribo. Okay, so we're at the salvage, which ties into the diseases. Okay, so